Good afternoon, everybody. Welcome to our workshop on terahertz. Title is Basics of T-ray Metrology and Time Domain Spectroscopy with Advanced Applications. I am Rahman, Chief Technology Officer of Applied Research in Photonics, located in Harrisburg, Pennsylvania. And this lecture series was formulated based on the workshop that I offered in other conferences, specifically Biosensor Bioelectronics in Phoenix, Arizona, 2016. SemiconWest, where I frequently have opportunity to join, but I had a keynote talk back in 2018. And also, I'm regularly joining Advanced Semiconductor Manufacturing Conference in Albany for a number of years. So many of these topics have been presented in those conferences. So the plan is, first we will go through some introduction about terahertz, and then the camera-less imaging details and applications. I mean, that is the main metrology application. And after that chapter, we'll come to time domain spectrometer and applications, or spectroscopy, I should say. And then optionally, I would like you to take on some challenge of your choice around the around the knowledge that you will be gaining from this lecture series. And of course, we will work together if you are interested. So the background is, none of us, we are social beings. So the semiconductor plays a key role in the world today. As you know, the entire world's economy is about some $103 trillion, of which electronics is 1/5. So some $21 or so trillion is the entire electronics industry related products. And that number is from 2023, so I don't know what is today. Probably would be a little better. Now, this slide was prepared for another talk where I gave on a gathering, but the screen, the pictures that you see, this is a webinar that I arranged inviting a State Department official. And the point I'm trying to make here is that United States have expressed interest of bringing developing countries into this supply chain so that the pressure on some particular country may be reduced. So because we are in a global society and a global economy, I think this is important to keep in our mind. But this will be the only slide talking about that. There will be no more talk on that. As I said, everything is electronics. Electronics rules our entire civilization. Any device, anything in your home, without electronics, probably 90% things will disappear. There will be no dishwasher, or there will be no under sink irritator and that kind of thing. That kind of basic things. So we owe a great deal to the advancement of the electronics industry, and how T-ray can help and complement. So I'll be using the word T-ray and terahertz, intermixingly, because terahertz radiation that abbreviated as T-ray. So it's like, X-ray, T-ray, and so on and so forth. So, but semiconductor industry is the one that we target a lot. And this is the background for that, where the semiconductor comes from. It comes from the very beginning, which is called sand. Sand has silicon. Silicon doesn't have any mine. It doesn't come from any mine. So you cannot dig it out of the ground. It has to be separated from sand. Sand is processed and made first a thing called, where is the laser pointer? So sand is processed and made into this kind of ingot, or as they call it, a boule, B-O-U-L-E. And this is a single crystalline silicon. And for electronics, this is very highly pure. You can have only one impurity atom in 1 billion silicon atom. So, 9 nines purity. And then this ingot is sliced and made into wafers, shown here, or disc. And these discs are then polished, made into N-type or P-type, on which the electronic circuits are, which is designed on a computer, of course. And at a later time, pattern is made, and then pattern is transferred onto these discs or wafers. And then each pattern is separated and made into a chip. This is a little bit more about that ingot. This kind of machine that is used, they call it ingot puller or boule puller. It's a high temperature technique. It's called Czochralski crystal pulling furnace. A Polish scientist some 100 years ago or so figured out how to make single crystal silicon from from silicon separated from the sand. So I'm going very fast through all of these things because sooner we go to the T-ray segment, is better. But you see the sand then processed into first thing called polysilicon, which is a metallic silicon separated from sand. And then single crystalline ingot is made. Then that ingot is sliced into a bunch of discs or wafers. On that wafer, lithography and other techniques are used to make the circuit. And then a fully lithography wafer looks like this. That was blank here on the right side. Then when all the devices are made, it looks something like that. But, this picture is specific to a given device. For different device, those squares that you can see will be smaller, bigger, or different size. Finally, those pattern or die on wafer, each of these little square is a device, but when it is on wafer, they call it a die. When they separate it, cut them singularized, and electrodes are connected, packaged, then it becomes a chip. And the chip testing is done over here, multi-probe electrical testing, but you will see with T-ray, we are going to change. At least we're going to propose to change that kind of technology. At any time, please feel free to ask if you have any question or comment. So with that background, let us move into the introduction for T-ray or terahertz radiation. So what is terahertz or T-ray? it is the energy on the electromagnetic spectrum, which is between the infrared and microwave wavelengths. So you see this wavelength scale or the frequency scale. Wavelength starts high, ends low, and then frequency is, of course, reciprocal of that. Starts low, goes to high. So 1 terahertz is 10 to the power 12 hertz. So the T-ray actually ranges from, a few 10 to the 11 to 10 to the 13. Particularly in our formulation, you will see it starts from 0.1 terahertz to 30 or so terahertz, a little more than 30 terahertz. So this used to call this band of spectrum used to be called as terahertz gap. Gap because there was no man-made terahertz source in the laboratory. And it has a fascinating history. A scientist named Dave Austin, not Austin, Austin, A-U-S-T-O-N, working at the Bell Labs, first demonstrated that you can generate terahertz or the energy in this gap by taking 2 electrodes on a insulating substrate, very small gap electrodes. And if you apply high voltage across that 2 electrode, and then excite that with a pulsed laser, then the charges will get into oscillation, and the oscillating charge always generate or emit radiation. That's the very basic mechanism, and he showed that it can, generate between 0.1 to up to 1 terahertz or so output frequency. So that's how we all got started with terahertz. And the reason is that it is a non-ionizing radiation, unlike X-ray, which can penetrate and go through different objects, including our body. But it also provides the X-ray dose, radiation dose, because it's an ionizing energy. But terahertz or T-ray is non-ionizing, even though it can penetrate through our skin or our muscle or up to a bone or something. But it does not hurt delicate tissue, or in case of semiconductor, delicate circuitry. And that's the reason that we are so excited about T-ray, because it can see or probe below a surface without breaking it non-destructively. But there is no downside. It doesn't hurt. It is not unperturbing energy. It does not perturb the sample that we are probing with it, including human tissue, and semiconductors and others. And yet we can measure their intrinsic properties unless we excite it from the outside impetus, then we can measure the excited properties as well. So we use it for many different applications. Initially, there was a very big thrust that T-ray can be used for, screening and security monitoring and all of those. That did not advance very much because of the pulsing. Terahertz technology has very low power. It depends on a femtosecond pulsed laser, and that femtosecond pulsed laser itself is an emerging technology, a very expensive and big piece of equipment that's needed for generating the pulsed terahertz. and yet it generates microwatts of terahertz power. And because of that, not much, applications have been developed with that terahertz source, and probably we'll have a little bit more about that. And the other thing is we need very high resolution for semiconductor metrology applications, where terahertz being a bigger wavelength, I'll come to that, is illuminated by the diffraction limit. So Abbe diffraction limit, meaning that Ernest Abbe, German scientist, established in 1873 that when you are imaging with a microscope, the image resolution cannot be less than half the wavelength of the light one is using for imaging. So in visible, if you think about some 350 nanometer to 750 nanometer, on the UV side, UV wavelength can go down to 250 or so nanometer. And half of that is, 125 or something. That is the smallest object UV can resolve. And visible light will be resolving less than that, bigger than that. But to be able to see the atomic lattice or some other delicate features in semiconductor, we need much, much better, much smaller ability. So that is one of the obstacles TRA suffered. And in fact, all imaging systems suffered, except for electron microscope, because electrons have wavelength in picometers, and can be also controlled by applied voltage. So that's why electron microscope can do the atomic lattice imaging. And as you will see during this course that we have been able to figure out how to do atomic lattice imaging with bigger wavelength. And then characterization of 0D or zero dimensional to three-dimensional nanomaterials is another area where we, believe it or not, there are materials which are zero dimensional. So we'll go through that as well. And in semiconductor, not only defects, but there are many, many things that we need to measure. That's the whole point of metrology. And also very high sensitivity spectroscopy when we come to the spectroscopy area, and detection of skin cancer and other kind of human tissue health monitoring application can be done. The last one, we're not gonna go that much until we finish the imaging, metrology, semiconductor application. I think that's where biggest focus is, because we're trying to get into that area where they can use it for very, very useful purposes. And then, of course, spectroscopy has a wide range of applications. And then we can go into the biomedical application. So, TRA or terahertz technology started in the mid-80s, as I said, by Dave Austin. But in the meanwhile, other people have been trying to do the same thing, and quite a few technique was proposed and demonstrated. The photoconduction or photoconductor technology is the legacy technology. As I said, that was demonstrated by Dave Austin. Then other groups, especially the Robert F. Kroll Jr. group in Rice University, they used the difference frequency generation technique, where they used two, because, avoiding the pulsed laser seemed a big deal. So Curl group, Curl, by the way, won Nobel Prize for buckyball structure, but his group also did work in terahertz. So they wanted to avoid the pulsed laser, which is, it's not easy to get a pulsed laser, femtosecond pulsed laser, not just regular, any pulsed laser. So they used diode laser, curve group, and the frequency of the two laser they used, the difference of the two frequency is the one that in terahertz range, which can be tuned. The terahertz frequency can be tuned. However, because the inorganic materials don't have very high Chi2, and mixing the pulse in organic material is becoming very difficult. So they still were in very low power, nanowatt to microwatts of power. They couldn't even come to milliwatt. So this should be, M for micro. I'll have to correct that. This is microwatt, not milliwatt. And if you're taking notes, make sure that you make it microwatt. And I'll be able to make this presentation available later when the book is ready. And still, it's a work in progress. So higher power is the milliwatt, not microwatt, not milliwatt. It's a mistake here, typo here. And then, of course, one can use the nuclear reactor or synchrotron, by a technical free electron laser. Undulating that free electron laser can generate terahertz. And that can give very high power because reactor has a lot of power in there, but it has a limited range. It cannot go very, bandwidth is very, very low. 1 terahertz or so at the peak. QCL have been quantum cascade laser, have been used, being tried for terahertz generation, but it's not very stable. It's not possible to buy commercially yet. They're still under research. So we use, our company and all our approach use a technique, what we call is a dendrimer dipole excitation. And I will explain a little bit of that. Dendrimer is a nanomaterial, a polymeric nanomaterial at that. So it has a lot of advantages for terahertz generation, but also we coined the term, silicon for photonics, because dendrimer can be an optical amplifier, optical modulator, waveguide, array waveguide grating, and all of those things can be made from this one material. Like silicon can do everything for electronics. So here, advantage is that we don't need a pulsed laser. We don't need very high voltage. In fact, we don't need any voltage for terahertz generation. And its output power as well as frequency range, both are tunable. But on the challenges, that is a new technology, so still not in the textbook, etc. If you find any book on terahertz, there are quite a few of them, but dendrimer dipole excitation is in none of them. So I think someone has to start writing that book. So with that, do you have any question or comment up until here?
Can you go back to the previous slide for a minute?
Yeah, sure, absolutely.
One maybe clarifying question about your technology, the DDE or dendrimer dipole excitation. On the right-hand column, I see something called dendrimer doping and polling.
Sure.
I understand doping part, but polling, I'm not sure.
Okay, I'll come to that.
Okay.
I think I have a slide on it, but if not, I'll have to add one for sure.
Okay, great.
Sure.
Thank you.
So, this is on the right side, Robert F. Carl Jr., Nobel laureate in chemistry from 1996. And this gentleman here in the yellow shirt his name is Sir Harry Kroto. So Harry Kroto, Bob Carl, and Deb Smalley, these three folks won the Nobel Prize in chemistry in 1996. And two of them, I was fortunate to, attend one of their reception in Dallas, Texas, quite a few years ago. I believe it was 2007. Yeah, 2007. So that's the date this picture was taken. And I had a very personal discussion with Bob Carl because his group, produced difference frequency terahertz radiation. So in an email, he wrote me, he and I had a little bit of communication. In one of them, he said, everyone knows that beta terahertz sources are important for scientific problems. So that's about the time when we generated the terahertz radiation from dendrimer dipole excitation. And I shared something with him. He actually was very appreciative. This gentleman, his name is Sean, I forgot it, Sean O'Neill, maybe, I forgot his first name. So Sean O'Neill was Deb Smalley's student, graduate student, when he figured out the buckyball structure. I'm sorry, he was the graduate student of Bob Carl, and he was the one who figured out the C60, buckyball structure, for which, of course, Bob Carl won the Nobel Prize, but he have been appreciated all along. He had a strong career at Texas Instrument for a long time. So anyway, he was present at that ceremony as well. His family was there too. So now let us, as I mentioned, that our company, Applied Research and Photonics, as we abbreviate it, ARP. Waveguide is the key for photonic integrated circuit. And that's what was our very thrust, to do the photonic integrated circuit as opposed to doing just, many other things, because of the fiber optic communication, the background that I had prior to starting this company. So we wanted to make that photonic integrated circuit, of which the waveguide in the photonics, waveguide can be treated like transistor in electronics. And probably will not come to that in this talk, but nonetheless, in 2006, we were awarded the patent on how we make waveguide with a dendrimer. And the key here is that, as you know, think about optical fiber. There is a core and there is a cladding. Without the core and cladding, fiber cannot work. So waveguides are made in the same way. First, they make a core, and then they put, covering on the sides to make it cladding. But the cladding must have a smaller effective index than the core. So what dendrimer does, the same dendrimer can act as the core and cladding. And that's a tremendous advantage for making waveguide. So anyway, with that, then, as I mentioned, DARPA was our kind of, they were interested in continuous wave terahertz generation. So we demonstrated that dendrimer dipole excitation, at the end of 2007, but for all practical purposes, 2008, when we also made our first spectrometer in our lab. And we had collaboration and projects ongoing. Every time we got a different project with challenge, we were able to find a better solution. For example, we had we had something going on with an organization called Semitech. Semitech was investing heavily to make EUV, extreme UV, for smaller feature size on this chip. So they said, if we have a line width of 1 nanometer, how are you going to detect that unless you have that resolution? So we were, because of that, we came up with 1 nanometer resolution imaging capability. Later, we had another project where we needed lattice resolution, and we figured out how to do the lattice resolution imaging or angstrom resolution imaging. So it's as you can see, expands. It's not a one overnight thing. We've been doing this 20 some years, and small progress. Finally, we are able to get better performance. And dendrimer dipole excitation is one I said before, which is dendrimer is a polymeric material, which is polymers are supposed to be long chain molecules, except in this case, it's a spherical molecule. And advantage is that it's a soccer ball-like structure, but you can have a smaller one, you can have a bigger one. And the number of valence sites depends on the generation. Bigger the molecule, more the sites available. So the polling comes here is that if we, dendrimer has the negative charges available there. So we need to produce dipole by doping. So when we, chromophores are the charge centers. I'll come back to that later. Chromophores, when chromophore doping is done and then that is excited, the dipoles are formed, then dipoles are excited by a pump laser of suitable wavelength, and then the dipoles get into oscillation. And as you know, any oscillating charge generates radiation. So that's how we generate Hertz radiation. And Don Tamalia here on the right side, who is known as the father of dendrimer, in 1983, he generated the first, he was successfully synthesized first spherical dendrimer molecule. And then I was fortunate to work with him when I was a postdoc. I worked on dendrimer since 1996 with Don Tamalia. We did quite a few basic study of dendrimer. We published in Langmuir and other places, but that's a different story. So
I have a quick question.
Yeah, please.
About the dendrimer.
Right.
You said it is spherical, like soccer kind of shape. It can be small and big, etc. How small, how big, and what kind of density? Can you give some ideas?
Sure. So this got mixed up, looks like. I should be able to do a better job. So dendrimer is a spherical polymer. It has a core, a central core, and around the core, molecules or substituents are attached, and that's called shell. So it's a kind of a core and shell structure. So now if I have a core and put the first shell, then they call it a generation 1. But the first shell can take another shell around it. Then now I have 2 shells and they call it generation 2 dendrimer. And so on and so forth. And it can go up to 11 or 12 generation. The size of the first generation, they actually count from 0th generation, but first generation is about 3.5 nanometer. Excuse me. And it keeps on going. I don't know what's for the 11th and 12th generation, but it's probably somewhere between 8-9 nanometer. So it can be bigger and smaller. And as you can see, the valence states increases by generation. So advantage is that we can attach chromophores not only around the surface, but also interstitial spaces. So the dipole moment is the charge separated by the length, right? That's dipole moment. But now the separation is not the same. In inorganic, if you are doping, then you will have a fixed lattice separation. So dipole moment is fixed, cannot be changed or distributed. But in this case, the dipole moment, mu, is a function of position because the length is not fixed length. So length has a distribution, therefore the dipole moment has a distribution. What's the big deal about that? As you can see from the energy level diagram, I don't know if you can see it, but several things are very important here to note. First off, we can control the dipole population by the doping concentration. And bigger the dendrimer, higher the dendrimer generation, more dipole can go in one molecule. So that, why is that important? Because the terahertz power depends on two things. One is the second order susceptibility, the chi2, and the pump power, laser pump power. But chi2 again depends on the dipole population. So if we can increase the dipole population, chi2 goes up. And this theta is the polling, as you can see, if I have cosine 90 degree, cosine has to be 0 for maximum, right? Cos 0 is 1, cosine 0 is 1. So that means this dipole has to be aligned in a way to minimize the theta so that we can get the maximum chi2. I probably have something on polling, but I'll show later. If not, I'll explain. So what's happening in here? First of all, we are getting a control of the dipole density. Then we are also getting a dipole distribution. Not all of them are the fixed like in organic lattice. And then we can, because of the high chi2, we have a better conversion efficiency, meaning that pump energy is converted into terahertz energy. So the conversion efficiency is also important. And if we do all of those things and the way we do it, we get up to 32 or so terahertz from 0.1 terahertz. So this is a very wide range of terahertz frequencies. And also the terahertz power, we have, as you will see probably at a later, well, I don't have any more on the terahertz generation, but we have, I will share the papers that we have on that. I don't know if I been able to answer Dr. Mazuda's question.
No, that's all right. That's good.
Okay.
Good enough to start thinking for me.
Thank you. Anybody else has any comment or question?
What is a common chromophore on the dendrimer?
Well, that's a very good question again. We have figured out one, but there are thousands of chromophore molecules out there. And because they are small molecules, they fit in the interstitial of the dendrimer. But we found one that works very well for us. That doesn't mean that that is the only one. So it's very difficult to answer specifically your question. One need to do a little bit of playing with it. Do one experiment. We did a lot of experiment initially, particularly the concentration, because it's a doping. That means that we cannot use 10 to 30% of that dopant material, right? It has to be small. So what is the optimum doping level? We didn't know. So we had to do some, quite a bit of experiment to figure out And every time you change the doping concentration, you have to pole it again. And poling meaning that initially all the dipoles are haphazardly aligned. Therefore, the net electro-optic coefficient is still just for the bulk, which is very small, like inorganics. But when you apply a field, the trick is here for doping. So first you make the dendrimer film, then the dendrimer film is elevated temperature near its glass transition point and hold there at that temperature. At that point, we apply an electric field, very high electric field, some 10 to 12 kilovolt. So we have a 20 kilovolt apparatus in our lab. And that's where we apply the high voltage electric field across the gap. Of course, nothing is touching. So the net effect is aligning the dendrimer dipoles with respect to that applied field. And when you have to measure the current. So we measure the current as we increase the applied voltage. And at some point, the current stabilizes. That means all the fields, all the dipoles are aligned. Because more alignment is higher current. But at some point, the current saturates. That means all the dipoles have been aligned. At that point, you turn up the heater so that the dipoles gets frozen in that aligned position, which then becomes the terahertz generator. So this is a routine work that we have to do every time we make a new source. But at the same time, the source at one point it is the source. In another configuration is the sensor for terahertz as well. So the pump probe technique will come in the spectroscopy segment. So I guess we came up to the end of the introductory part. And for today, probably we utilize the hour. So we probably can stop here. And sometime next week again, we can start right here.
Sure. I have a quick follow-up question about
please.
Using the pump laser. And what kind of power you are using for the pump laser, and what kind of output power you're getting from excitation? Yeah, right. I think you mentioned something earlier, but I'm trying to correlate.
Right. So maybe I should stop sharing now and go to the Q&A. We are still recording. So one thing good about dendrimer terahertz source is a non-absorbing system. That means most of the pump energy are converted into terahertz radiation. There's a little bit of wastage because of the reflection and transmission, all of those things. But we get very high conversion efficiency from dendrimer because it does not heat up. It's non-absorbing, meaning that the pump energy is not heating up the target. But that said, our source remains in the CW about 220 to 230 milliwatt. That's the source energy or source power. However, when you build the circuitry of the spectrometer or even the imaging system, the sample sees maybe about 10 milliwatts of power. But also it depends on 10 milliwatt power is reflected from a standard mirror. But if we put a biological tissue, for example, it's going to be microwarts of power, reflected power. Or if you put a semiconductor wafer, it's going to be in milliwatts. It's not 10 milliwatts anymore. But that's what we need, because we don't need very high power. First of all, high power for biological tissue is not good. Even though it is non-ionizing, it may still Actually Jefferson Lab folks did an experiment that said if you are applying about, close to 1 watt of terahertz power, that will break the DNA. So smaller power is better. And the same thing will be true for delicate electronic circuit as well. So the whole point is probing the sample without perturbing it. And that's where the small power or low power is important, but not as low as, difference frequency where it cannot do nothing, or even the femtosecond pulse laser converted power in the microwatts. That's not good enough either. So we need from microwatt to few tens of milliwatts of power is good. It's a sweet spot for a majority of the experiments. But that said, you always can increase the power or decrease the power. The instrument has that ability via an aperture, so we can adjust the power needed for a particular experimental situation.
Right. So this is a naive question. I have not studied enough, but dendrimer, the dipole you are creating from, are you using in a solid state or a dissolved or liquid condition?
Yeah. No, this is not solid. This is all liquid phase. And that's an advantage. If it is inorganic, we cannot do the liquid phase doping. But polling is not liquid phase. Polling is, of course, after the film is formed.
By the nature of these dendrimers, are these organic or inorganic in nature or something in between?
No, these are the dendrimers are organic molecule.
Organic molecule.
This is subject of an totally organic chemistry. However, the good thing, we have been fortunate that when you dope the dendrimer and we make the film is actually harder than silicon. It's still flexible, but when we try to make waveguide out of it, the same recipe they use for silicon is not useful for dendrimer. So that was one of our roadblock to create dendrimer integrated circuit. We have not been able to do that yet, but now we know how to do it, except we haven't been able to do that because, for terahertz generation, we found another way of doing it. So, which is more reliable. And in another slide or so, I have a slide to show how stable the terahertz power that we generate from dendrimer, or I will have to add at least if I don't have it.
So these dendrimers, are there any double bonds in the polymeric structure?
There are.
There are, okay.
There are.
Thank you.
There can be even it's almost, as you know, in DNA, although DNA has even triple bond, but those are hydrogen bond, and these are not hydrogen bonds. So these are the bond between the carbon and the nitrogen. So there is nitrogen and so amine group is the substituents. So the bond between the carbon and hydrogen is replaced by nitrogen.
The customer processes the sample by themselves, so they apply the dendrimer themselves before the commercial system.
Yeah, so good question. When you are, I'm going through the details of terahertz generation, but once the terahertz source is there, samples are totally different. Then you are dealing with only the T-ray. No dendrimer comes into play. Dendrimer is working in the background, producing the T-ray, and T-ray is being shined on the sample that you want to measure in a non-contact fashion. So I'll show you the instrument in the next lecture, how circuits look like, how these samples are hold and probed. But yeah, dendrimer has no more role, other than generating the terahertz radiation.
Yeah, I interpreted the slide as sample, maybe a thin film of dendrimer, and as a function of angle, the T-ray would produce the second order effects.
No.
Okay, thank you.
Yeah, it's like your.
It's not that.
No, I understand.
Okay.
It's like your flashlight. You generate the light, and light shines on your sample. That's what you see.
Okay.
Yeah, but it's a very good question though. I have faced this question more than once. That do you have to have dendrimer on the sample for the terahertz generation? And the answer is no. It's a source by itself in its own world, and the radiation. But radiation can come either free space, or we can also put it in fiber. So we have set up with fiber coupled, and that has an advantage, and I'll describe that in the next one.
Great, thank you.
Thank you.
You are welcome. So with that, we'll close here for today, and if you guys are okay, then next week, same time.
Okay.
Good. I'm good.
Okay, wonderful.
Thank you.
Okay, so let's stop the recording. Let's stop the recording. Oh, here we go.